restart recording? Okay, good. So let's go to the, can you see my screen, people? You see my screen, people?
Yes, doctor.
Okay, good. So let's go to what is more interesting, right? To the forced vibration part. So here. Now, we have to consider that two things. First, that there must be somehow some excitation. And of course, we know that since we are going to have probably some sort of resonances, then we should be careful because we should include also damping. Okay, so what I'm saying is this, okay, for damping, see, right now, we're going to be doing is simply this is going to be just a percentage or a certain value. I think it's 0.03. It's just an assumption. Okay, now, when we do, next, when you come for the lab session, what we can do, we can move this thing and allow it to vibrate. And from there, we can calculate this parameter, okay, using the logarithmic decrement. But right now, we don't have the time. We just do this. Let's take this. That's it. Now, this, remember, is equal to, do you remember what is this equal to? This theta? No, z, this is z. Anybody? Equal to what?
Damping coefficients over raised quadratic fourth mass multiply the coefficients resist. Sorry.
Okay. I don't know, but I prefer to do it like the 2m omega 0. And the problem is that here I have 3 omega zeros. So I just said, okay, let's take the first one. So it's an approximation for the first one. And that's it. And how about m? We just take the full m. And let's see what happens. Okay. In this way, we could take a reasonable value for C. Okay. Otherwise, I would have to be guessing too much. Just start. After doing that, yeah, we're ready. We can go on and include the damping. So we can say that if we have a damper, say it's kind of strange, right? Because we have this point, the damper is here, and this is the other point. So this is ui of t dot. And this guy here is ui plus 1 dot. And this is c sub I. So what we're saying is just that the force developed here is just proportional to the difference of these velocities. That's all. It's just a model. So we just simplify it in this way. Okay, so remember that here we have similar the spring. So in a similar way as the spring, we can establish the forces from the dampers. Okay, now finally, for the excitation. Ms. Freire, do you have any question? No? Okay. Okay, no problem. For the excitation, Okay. Okay. And the problem is that the end, let's suppose that this is the foundation, is moving like this. And the first mass is connected the foundation through the spring and the damper. So for the sum of the forces on this one here, okay, we can say that, okay, now if this moves to the right, an xt, and this moves to the right, a u1, okay, then some forces will be generated from these two. And this will consider x. But x is known, okay? And of course, x dot is also known. So x, we can take it as an amplitude times e to the I omega t. And x dot, it's going to be I omega x dot e to the I omega t. Okay, now let's do quickly, let's do a free body diagram as one. Okay, now on the right hand side, let's suppose I have this force and this force from the spring and from the damper. And similarly, on the left, we have this and that for the spring and for the damper. This is U1, which depends on time. So now, Ramon, tell me, this force here from the spring, this would be the spring number 2. What is going to be this force here? Please look.
This
please.
force
Okay, go on.
is K2 for U2.
Yeah, but remember that if U1 moves, it's going to affect also this force here. Yeah, we're saying is that if we are here, this is the spring that we are considering, and this is the mass that we're, I'm sorry, this is the spring that we're considering, right? But if this moves, this is U2 and this is U1. But if this one and this one moves, they both affect these forces. So here I should have U2 and also U1. Mr. Galarza?
Yeah, it should be K2 U1 plus K2.
U1
Plus U2. So
remember, if you move U1, the spring compresses. If you move U2, the spring elongates. So the effect will be minus.
U2.
Ms. Pinkai, could you give me this force here?
That one is for the damper, right?
Right, for the damper.
It's G1 times U1 dot.
But remember that now the X, the base foundation, it also moves. Right now, X of T is not zero. So the foundation, this is moving also. Mr. Zamora,
It will be
what's missing here?
minus X.
Minus X.
Yeah, I think so. That's yeah.
Now, this is velocity, this is displacement.
Dot.
You're adding potatoes and tomatoes. You cannot add them up. There you go. Please, always units. Okay, I'm not going to write everything. I mean, you have to complete the thing. But then you have these four forces applied on the mass one. And remember that the terms that have X or X dot, you know them. So you can move it to the right-hand side. Those are the equivalent excitation. Okay? Those are going to be the equivalent excitation. Now we're ready. So we have M U dot plus C plus K. And on the right-hand side, we're going to have an equivalent excitation, whatever it is, times e to the I omega t. Let's put it this, because there's going to be some phase shift between them. Because you're going to have X and also X dot. There's going to be 90 degrees of phase shift between them. So in general, you're going to have something like this. And of course, if this is the excitation, e to the I omega t, okay, then the solution, I'm sorry, I cannot write this solution. The solution is going to be U. It's going to be a vector of amplitudes, which we do not know, times e to the I omega t. Okay? We can cancel e to the I omega t when we replace, and we can say that the matrix D now, it's a little bit more complex. The vector U is equal to the vector equivalent forces. Now, this is your D matrix now. And you can solve it. Remember, okay, if you have the matrix to the left of this vector, when you pass it to the right-hand side, it has to be to the left of this vector. Be careful. Okay, in this case, this is 3 by 3. This is 3 by 1, and the result is 3 by 1. Okay, and the thing is that when we calculated natural frequency, we were trying to determine the frequency at which the determinant of this was 0. When you calculate the inverse, you have to divide it by the determinant. So every time you get omega gets closer to the one of the natural frequency, the determinant of D is smaller. It's not completely 0, because in this case, we have the damping, but you can expect to be smaller. So the quotient will increase. That means that every time you get closer to a natural frequency, the response of the system, you can expect to increase. Okay, now this is an operation that you can complete using complex arithmetic in Excel. But yeah, you can do this. Any questions about these people so far?
I have a question, doctor.
Yeah, go on.
How to calculate this force equivalent?
For example, when you write this equation, okay, you can say summation of forces in the x direction is equal to mass times acceleration. And here you have this pointing to the left. So you're going to have minus C1 U1 dot minus X dot and many other terms, right? In this case, you're going to have 3 more terms. And this is going to be equal to M1 U1 double dot. So you're going to have this C1, this term, you know it, times X dot, and these terms, you also know it. Since you know that term, you put it on one side. All the terms which include U1, U2, or U3, you put it to the left. Why? Because there's something that you try to determine that you don't know yet. So this term, C1 X dot, will be part of the excitation.
Okay, okay.
And also here, you have to do it. I'm not going to do it, but here, you also are going to have X. So those 2 terms, they pass to the right-hand side because you know them. That will form part of the vector of equivalent excitation. You have to be careful because they have some phase shift. The amplitude of those terms will have some phase shift between them. Delgado?
Yes, doctor, thank you.
Okay, no problem. Here, this is something that I pretend to do when we come back to the university some weeks from now. Can you see the video, people? Can you see the video?
No, doctor.
No, just to image. Just we can see.
Let me see if I can. See if I can do something. Okay, I can try to see if I can. Did you see the image of the video now?
Yes.
Okay, this is the experiment that we're going to be developing, okay? Here, well, this is the part of the shaker. It's located horizontally. So the excitation goes like that, okay? And it identify, this is the structure or the model of the structure, which simulates a 3-story building, okay? So here I have 1, 2, 3 masses. We can change those masses so we can obtain different results. And here, what we did was we installed 2 accelerometers so we can register the acceleration. And here I have 1, 2, 3, and 4 strain gauges. So we can record the strain at these different positions, okay? Remember, we had the equations for the beam bending. So you calculate the response, and from the response, you could calculate the strain. So you can compare with the experimental results. And what we did was Isaac set up the system so that we started with a low frequency and we covered the 3 natural frequencies, okay? And we moved very slowly. I think it was 2 or 3 minutes. In your case, when you come to the university, we're going to do it slower. So the problem is that when you change rapidly, when you get close to the resonances, there can be some strange responses suddenly. So that will probably distort the results. But that's what you're going to see. Okay, you're going to see that at the beginning, the motion of the foundation has very low frequency. And then as the time goes by, the frequency of the excitation increases. And you'll see. That's very low frequency. The amplitude probably it's about what? 1 centimeter at the top. 1 centimeter is large. But then you see that the amplitude of the top decreases. And then you see that the frequency increases and the amplitude is smaller. You see it? That's resonance, probably with the second mouth shape. Response decreases. There is a large response, do you think? Okay, so that's what we're going to be analyzing in detail when we return, okay? So in that case, what you have to do is, for the analysis that you need to do is, again, in an Excel, you have in a cell, the excitation frequency, then you have a 3x3, this is Excel. So in each one of these 9 cells, you can evaluate the dynamic metrics, but you have to be careful because these are complex constants. Okay, and each one of these depend on, well, not all, but some of them depend on omega. Okay, on the right hand side, I have the equivalent force. And the equivalent force, remember, that also depends on omega, because the x dot, okay, x dot through the damper in between the foundation and the first mass, the C1 multiplied by x dot represents an equivalent force. So when you differentiate, you have omega. So omega will be here too. So you're going to have omega here and omega here. And finally, from here, you can calculate U1, U2, and U3. And these are complex. So after we calculate the complex amount quantities, you can calculate the amplitude, which is the most important part. The phase is going to be very important because when we analyze the experimental results, for example, you see that in some points, this goes to the right and this goes to the left, right? And we can see that in here, in the phase shift. So when one goes up, the other goes, one goes to the right, the other goes to the left. So we can check that, or we can compare the experimental results with the analytical results, comparing or considering the phase shift between the U1 and U2 and U3. Okay. And then what we want is a plot of omega. And here we could have either U1, U2, and U3. Okay, so here you have omega 1, omega 2, and omega 3. So you're going to have an increment here, an increment here, and an increment here. According to the mouth shape, each one of them will vary differently. So it's going to be quite interesting. So you're going to have 3 plots, each one for each one of these degrees of freedom. So you have several values here. And try to plot this in, for example, in millimeters. Okay. People, do you have any question?
Doctor, I have a question. This is the frequency we have a resonant antithesis system.
Yeah.
Yeah, okay.
You have 3 regions of resonance. When this is the shaker moves this foundation, okay? And this moves in this direction. Let me change color so you can see the, okay. The shaker is moving this in this direction. Okay, and this amplitude is, I think it's 1 millimeter, peak to peak. So this means that if this is the motion is like this. From here to here, it's 1 millimeter. So the amplitude is 0.5 millimeter. And the frequency changes. It goes from a very low frequency to a frequency which is higher than the excitation frequency. So we cover the whole 3 regions of resonances. Okay, so every time you get closer to one of the natural frequencies, you get into a resonance region and you can expect an increment in response. After you come out of the resonance, the response decreases. When you go into the next region, or again, increases the response, and when you come out, you decrease. And then for the next one. Okay,
Thank you, doctor.
no problem. Any other question, people? Let's do a survey here. Enrique, did you start homework?
Hello, I check every homework and I try to resolve, but I don't formally to beginning.
You haven't not started yet. Okay.
No,
Okay.
just to analyze the formulations.
Okay. Miss Freire,
Yes, I have started the homework. I have done until 3, but I haven't done the part that says on a point B. Well, I do the first 2, but
Okay.
I'm doing right the 3, and I'm missing totally the 4.
Mr. Ramon, have you started homework?
Only the first and second question.
That's about the 24th of May.
Yes.
And how are you planning to organize your time during this for this semester, Mr. Ramon? Can you share with us?
I have a full-time only study because I only see dynamic design 1.
Ship design.
See, ship design.
Okay. So you have no excuses. You should be able to complete both courses successfully. You have no
Yes.
excuse. Ms. Lopez, have you started the homework, Ms. Lopez?
Yes, doctor. The third exercise. Complete
How many classes are you taking, Ms. Lopez?
dynamic and ship design.
2. So you should be able to, I mean, you should have enough time for both. Do you?
I try.
Mr. Zambrano, have you started the homework?
No, doctor, I have not.
Okay. Do you know that there is a homework?
Yeah, I do know.
Delgado, have you started the homework?
Yes, I started. I am doing the sectors,
Okay.
but I have a question, doctor.
Go on.
For calculation the stiffness, we have calculate each one for the elements,
Yeah. For the legs.
but yes, we have 9 elements or
No. We have only 3 elements. Here. See. Let me go back. Here, for example. Calculate the equation of the third mass. There is no U1 here. The equation of motion of the first mass, there is no U3 here. That means that there are some elements in the dynamic matrix which are not going to appear, are going to be 0. Is that your question, Mr. Legal?
Yes, yes, thank you.
I'm not going to tell you what elements, but yeah, you have to be careful because when you have the equation and you put the terms into the matrix, you have to be careful to identify which terms are going to be equal to 0. But yeah, some terms are going to be 0 in this case.
Okay.
In this case.
Okay.
But in general, you see that, for example, in the first equation, you have, that's the equation for U1, but you have U2 in there. So the two are connected. In the second, you have the 3 degrees of freedom. What I'm saying is that you cannot solve U1 independent of U2, independent of U3. You have to solve the system as a whole. Okay, people, that's 5:30. Remember, at 6 p.m., we're going to have a presentation, a conference from Lisette Salazar. She's a PhD student at the University of Liège, and she's an sport graduate. And hopefully in 40 years, she was going to be a Dr. Salazar. Okay,